Alright, so read the problem.
A car with a mass m is rounding a circular horizontal curve with a radius r. The coefficient of a static friction for the tires on the road is static.
So let's say it's a right-hand turn, right? There's the road.
That's what I was confused about. Like,
There's the car. Well, you could do it either way. It wouldn't matter. It would come out the same. So right turn. So where's the center relative to the car? Where's the center of the turn?
It's going to the right.
Okay. So the acceleration, therefore, is to the right, right? And the force diagram is, let's see. You got weight. Yeah.
Equal? We didn't know. I'm assuming.
Well, I know you can figure it out. Is there any acceleration up or down?
No.
So they have to be, these forces must therefore add to zero. I'm only using second law. I'm using Newton's law in the vertical direction to answer that. Third law is different. Third law is about each of these forces. You would never talk about third law when you're doing a force diagram, because when you do a force diagram, you choose a system. But every force has an equal opposite pair. Like the Earth's pulling on the car is pulling on the Earth. That's a third law pair. The surface is pushing up on the car, well, the car is pushing down on the surface. That's a third law pair. But that's not relevant when you're using Newton's second law to solve a problem.
Especially if acceleration is like to the right.
Yeah, the connection between acceleration and net force, that's different. That's first and second law. You guys good? So, is there like snacks or something?
Right now, I don't think so. No.
Yeah. Okay. All right. So, you're missing one more force here. What keeps the car from sliding to the left when it? And from a bird's eye view, if there were no friction, I'll do bird's eye view here. Yeah. So here's a bird's eye view. Same right-hand turn, right? But this is from above, and here's the car. Okay. What do you guys think would happen if the road was icy? Which way would the car move? Yeah, it would just go straight. That's what would happen if it was icy. What is preventing the car from just going straight, from slipping? That's right. So that's how we know there's static friction to the right. And it's holding it in the turn. It's this way, in the same direction of your acceleration.
But I thought the static friction was supposed to oppose the direction of the movement.
That's only when you're sliding. That's kinetic friction.
Okay.
Static friction is way complicated. And now with my vector sum diagram, when I add my vectors, I got normal. And I'm using this rear view. I'm using this rear view viewpoint, not the bird's eye view, right? All right, from behind. And then you got weight going down, right? I'm going to call weight mg. I'm going to call friction mu normal. I'm going to check with my your reference sheet, make sure I'm doing that right. I'm going to call normal up. Yeah, if you look on your reference sheet, it's the 1, 2, 3, 4, 5th one down. Force of friction is less than or equal to mu normal. And when you're dealing with static friction, the maximum static friction can be is mu normal. That's why there's a less than or equal to sign on your reference sheet. 0. Sorry.
That makes sense.
I don't mean to be snappy. Which way is your net force?
Right.
Yeah.
This is head to head and down to 10.
Good. And that's the same as the direction of your
Acceleration.
which makes labeling this MA makes it legit, but I can do better. If I'm moving in a circle with constant speed, I can assume that my centripetal acceleration is what? This is your next equation in your reference sheet. What's your centripetal acceleration?
So square. No.
Yeah.
Isn't it?
That's it. And it's right here.
You don't include m there.
Well, no, this is just your centripetal acceleration. Our net force is m v squared over r.
Centripetal.
That's ma.
Wait, centripetal is basically like.
Centripetal means
center in the forward, right?
this is the magnitude of acceleration vector towards
The center, right?
center when you're moving in a circle with a constant speed. So this only works when moving in a circle. I'll just say steady speed. Make sense?
Yeah.
That's only time you can use this. Okay? So I think pretty much anything we could solve for is right in front of us now. What are we trying to find? What are we given? Let's say it that way. What are we given here?
Mass.
Okay, slow down. Given mass. What else? Radius. What else?
And you know coefficient of a static, which is
Coefficient of static friction. This is coefficient of static friction. What else?
that's pretty much it.
Yeah, I think that's
Is that it?
Yeah.
Okay, and what are we trying to find?
speed.
Find V. This is like the people who put the signs up on the road have to calculate the speed first based on physics. So they are doing something like this to find the speed. So there's two equations I can write from my vector sum diagram. I could write normal equals mg. What's the other one I could write?
Mu static normal equals
Good.
mh.
Mu static normal equals m v squared over r. Good.
So that.
Now I can take this m and plug it in, mg and plug it in there. So I get mu static normal. Whoops, my bad. Let me go back a step. Bam. Mu static times mg. And I'm going to multiply by r.
okay.
And I'm going to divide by m and say that's equal to v squared. And I'm almost done.
Alright.
And then I'm going to say v is actually the square root of all that junk.
Yeah.
Which was, wait, I don't have to worry about mass. Look at that.
It cancels out, right?
Isn't that beautiful? The mass of the car doesn't matter when you're finding out that speed to take the turn. That's cool. So the speed is mu static, which is extremely important. I think they're going to assume everyone has good tires. Very important on a car. Mu static times radius of the turn. Smaller radius is way more dangerous, right? You're going to have to go way slower. And then G. So I could ask you a series of questions right now very easily. And you could also rewrite it as this if you want. In a way, this is simpler. So if I asked you, like, what would happen to this speed that you can take the turn without sliding, right?
Yeah.
What happens to that speed? How much does the speed decrease when your coefficient of friction goes down by 1/4? Yeah, you have to drive half the speed if your coefficient of friction goes down by 1/4.
That means it's going slower or faster?
You have to slow down if you have less coefficient of static friction. Say the road is wet, right? And when the road's wet, the static coefficient's more like 0. I mean, it's probably 1/100th it was the day before when it was dry weather. So if your coefficient of friction goes down by 100 times, 1/100th what it was before, how much slower do you have to go then?
10 slower?
Just 10 times slower. Square root of 100. What if you tripled your speed? Yeah, how much more coefficient of friction would you need? Look, I can just take any equation and I can write, well, v squared is proportional to mu, right? Well, if you triple your speed, how much more coefficient would you need? Speed is squared, so you would need 9 times the static friction coefficient. You can take other variables out, like v squared is proportional to r, right? So if you drove a curve 10 times faster, right? How much more radius would you need that curve to have? Isn't that crazy? You need a much gentler curve. If you speed up just double, your radius of your curve has to go up how much? Yeah, that's amazing. So you need a much smaller changes in direction when your speed goes up. So speed has a dramatic impact. And then gravity field's not that interesting because you can't like change it easy. But again, v squared is proportional to g as well. You guys good?
Yeah.
And you can do that with any equation. You don't even have to necessarily know what these things mean. And you can still reason through mathematically and answer questions correctly. You know, and actually the mathematical reasoning can help you understand the physics a little more sometimes. Anyway, I hope that helps.
Oh yeah. You forgot to put G there.
Oh, where?
Like after the M.
Oh, you are awesome. Oh, it's
Yeah, right?
MG went here.
Yeah, and yeah. So
It was right there. It's here.
just got substituted there. M.
It's in there. N was replaced with MG. But you're still awesome.
And how do I know like when to use this? When to apply this to it?
UCM means an object is moving how? No, it's not moving to the center. Read this. V squared over r is your centripetal acceleration only when you got to be moving in a with a
Constant speed.
there you go.
So with the constant speed moving on.
And that turns out to be a constant acceleration, which allows us to use second law and replace our net force with ma.
Wait, constant velocity?
Mr. Day, you have a first aid kit?
Uh-oh. Let me check this out.